Page 4, nuclear notes. So symbols used in nuclear chemistry, table O. It provides you the name of common particles used during nuclear reactions, the notation of how you are going to see these particles represented in a reaction, and then the everyday symbols to shorten the name. For all of these particles, notice in their notation there's a number that's written as a superscript. That top number, that superscript, represents what we're going to refer to as the mass number. And notice each one also has a subscript, a bottom number. This represents the atomic number. And these two numbers, the mass number and atomic number, show us how the nucleus of the unstable radioisotope falls apart. Okay? The main particles you need to be most familiar with are alpha, beta, and the gamma radiation. So if you take a look at this electric and magnetic fields diagram, you have a radioactive substance giving off an alpha, beta, or gamma form of radiation, and it's passed between charged plates. Notice that the beta rays bend up towards the positive electric field. The alpha particles bend towards the negative electric field, and the gamma rays pass straight through. It does not bend upward or downward. So this gives us information about the charges carried by each of these particles. So the alpha, it's attracted to the negative plate. So therefore, the alpha is a positive charge. The beta is attracted to the positive plate. So therefore, that beta particle is negative. The gamma was not attracted by either plate. So it's not attracted at all. So therefore, the gamma carries no charge. You need to remember the idea that opposite charges attract and like charges repel. So using that idea, so if you see a diagram of the electric and magnetic fields, that if the beta is shown attracted moving towards that positive plate, it must be negative in nature. The alpha particle, when it comes to those negative or those charged plates, it bends towards the negative plate. So therefore, the alpha must be positive in nature. And since the gamma is not affected by either, it just passes straight through, the gamma must not carry any charge. The other part of this, the last diagram here on page 4, it represents the penetrating power of the different forms of radiation. So here we have the alpha. And the alpha, as it comes across tissue paper, okay, it stops passing through. So the alpha particle is stopped by simple tissue paper. The beta particle, I'm going to put the minus sign there, okay, as it approaches the tissue paper, it passes right through the tissue paper, and then it comes to aluminum foil, and it is stopped in its movement. Gamma, on the other hand, it passes through the tissue paper, it passes through the aluminum, it passes through a concrete wall, and it doesn't stop its motion until it hits lead. So gamma is the most powerful or the strongest of the radiation, and the alpha would be considered the weakest. Its movement can be stopped simply by tissue paper. Alpha and beta, okay, notice that they have mass, a mass of 4, and, well, the beta has no mass, but it has an atomic number, where gamma, no mass, and a 0 for atomic number. Alpha and beta, they are considered actual particles of matter like an atom. Gamma, no mass, no atomic number. It is pure energy. So one of the things that I would do is I would go back up and on your reference table, I would put strongest and I would write pure energy. Alpha, weakest, but alpha and beta, I mean, it has the word particle. They are particles, so they do affect mass, whether it's affecting the number of protons or neutrons.